So for part B of this example, we're asked to find the resultant force using Cartesian force components. Part A, we went through the vector addition process where we formed our parallelograms and our vector triangles and used the sine and cosine laws to get our vectors and our angles. In this particular case, now we're going to be working in our standard XY coordinate system. So just to put that down on paper here, we recall that we have a positive XY coordinate system with X going to the right and Y going up, and then we have a rotation that's also defined as positive theta, and this is our positive coordinate system, our positive quadrant of a coordinate system. X goes to the right, Y goes up, and theta rotates counterclockwise beginning at the x-axis. If we use this coordinate system during our calculations of our force components and follow the sign convention laid out there, everything will work out for us in terms of additive properties. So to begin this problem, let's draw our free body diagrams. Free body diagram. And this we also just call FBD. Now this basically starts every problem. Up here we have our hook and force system. So let's simplify that a little bit. First, let's sketch out our axes here. Here's approximately our y-axis and our x-axis. And then we have a force here, force 1, acting up and to the left. So this is force 1 is equal to 8 newtons. And it's acting with this 45-degree angle. We have force 2 acting down and to the left of 5 newtons, and it's acting at 30 degrees off of the horizontal. And finally, force 3, use blue for that, is acting down and to the right, and it's acting at 20 degrees off of the vertical here. Now you'll notice that none of these angles are defined in terms of our theta as positive acting off of the x-axis. So if we want to get the real theta for force 1, we need to add 90 degrees to that. The real theta for force 2, we have to add 180 degrees, and we have to add 270 degrees for theta 3. And we'll do that in a little bit. For now, let's break this down into what we would consider our Cartesian force free body diagram. So there's our particle. That's where all the forces are acting. And we've got a force 1 y acting up, and we've got an x component of that acting over. Now I'm drawing that as a negative force because I know the x component of that force is negative. It's not an unknown to me. If it's unknown, I'll draw it by default as positive. But if it's a known value, I can draw it with as much detail as I know. And I know it's got an x component that's acting to the left. If we look at force 2, we have an x component acting to the left, F2x, and we have a y component acting down, F2y. And then force 3 has a y component acting down, F3y, and this time it has an x component acting to the right, F3x. So now if we want to determine the magnitudes of those x and y components using the force vector magnitude and their angles of rotation, then once we have the magnitudes in the x and y direction, since x and y are defined as orthogonal or perpendicular to each other, we can simply add up all of the forces in the x direction and all of the forces in the y direction to get our resultant x and y force components. So before that, we need to calculate our angles, theta 1, theta 2, and theta 3. Let's draw those on this diagram here. We can go here and say that this is theta 1, This is theta 2, and all the way around is theta 3, starting at the x-axis, rotating counterclockwise until we intersect our force vector. So let's determine the magnitudes of those, and it's quite simple. Theta 1 is equal to 90 degrees plus 45 degrees, and this is equal to 135 degrees. Theta 2 is equal to 180 degrees plus 30 degrees, 210 degrees. And finally, theta 3 is equal to 270 degrees plus 20 degrees is equal to 290 degrees. Now, I'll just put an aside here because I've seen this happen too many times. I'll put a little squiggly line around it so we know it's not part of the problem. Make sure your calculator is in degrees, and make sure you know how to change it from radians and gradians to degrees in a test scenario. That's not something you want to learn on the fly, and I've seen it happen, and if you're not paying attention you can get some pretty random numbers that you might not catch until the end. Now that we have those, we can begin to find our force components, the magnitudes of our force components. So to do this, we're going to use some basic trigonometry that we covered before. So we're going to find the force components. And we know that Fx is equal to F times cosine theta, and Fy is equal to F sine theta. And this is true only if we follow that sign convention. Otherwise, we're going to have problems with the pluses and our minuses if we don't follow that. Theta is positive beginning or rotating counterclockwise beginning on the x-axis. And if we follow that sign convention, we can come up with an Fx. And if that Fx is negative, that means it's acting to the left. And if it's positive, it means it's acting to the right. And the same principle applies to Fy. So let's begin with our x components. And here we can see that F1x is equal to F1 cosine theta 1. This is equal to 8 cosine 135 degrees is equal to F1x is equal to minus 5.657 newtons. F2x is equal to F2 cosine theta 2 is equal to 5 newtons cosine 210 degrees. And this is equal to minus 4.330 newtons. So this minus sign is working for us. It's telling us that that force is going in the negative direction, as defined by x is positive to the right. And F3x is equal to F3 cosine theta 3 is equal to 11 cosine 290 degrees. And this is equal to positive 3.762 newtons. Now we notice, if we look back at our drawing that we did before, in terms of our free body diagram for F1, 2, and 3, x and y components, we had F1x is negative, F2x is negative, and F3x is positive. And we just calculated F1x is negative, F2x is negative, and F3x is positive. So everything seems to be working out so far. Let's find our y components. F1y is equal to F1 sine theta 1, and this is equal to 8 sine 135 degrees. And this is equal to plus 5.657 newtons. We see it's the same magnitude as F1x. The sign's different, but the magnitude's the same. That makes sense because it was acting at a 45-degree angle. So hopefully the magnitudes are the same. F2y is equal to F2 sine theta 2 is equal to 5 sine 135 degrees. And this is equal to minus 2.5 newtons. And F3y is equal to F3 sine theta 3 is equal to 11 sine 290 degrees. And this has a value of minus 10.337 newtons. So let's check those. We have minus 10, minus 2.5, and plus 5.65. Well, F3y should be negative, F2y should be negative, and F1y should be positive. That's okay. F3y was minus 10. Well, we have F3 is 11. Most of it's going down, so that makes sense that it's minus 10. And if we look at F1, we said that this is 45, so the x and y component should be about the same. And then F2 was 2.5 in the y direction and 4.3 in the x direction, both negative. So we have 30-degree angle. Most of the force is going in the x direction. It makes sense it's a larger magnitude. Some in the y direction, and both are negative values. So all of this indicates that we're on the right track. Now, once we have that, we're ready to find our force components of our resultant force. So find resultant force components. And this is quite simple. Since we have these orthogonal forces now, we can add as many of these force vectors together as we want without having to worry about angles. This means that our resultant force in the x direction component is simply equal to the sum of forces in the x. And this is equal to F1x plus F2x plus F3x. So FRX is equal to minus 5.657 minus 4.330 plus 3.762. And this is equal to negative 6.225 newtons. Now we can do the same with the y. Resultant force in the y direction is equal to the sum of forces in y, and this is equal to F1y plus F2y plus F3y. So our resultant force in y is equal to plus 5.657 minus 2.5 minus 10.337. And this is equal to negative 7.180 newtons. So now we found the magnitudes of our force components in the x and the y direction for our resultant force. At this point, we're interested in determining the magnitude of the resultant force itself and the angle at which it acts. So let's find Fr as a vector. Well, to do that, let's sketch out our force components. We have a negative Frx is equal to minus 6.225 newtons, and Fry is equal to minus 7.180 newtons. So if we use our knowledge of vector addition, or really just Pythagorean theorem here, we can find Fr. And we know that since we're dealing with orthogonal components, we have these 90-degree angles that show up in this these force triangles. So we can say that Fr is simply equal to the root of Frx squared plus Fry squared. That's just Pythagorean theorem. Fr is equal to the root of negative 6.225 squared plus negative 7.180 squared. And we know that when we square a negative number, it turns into a positive number. So we can take the root of this positive number and get Fr as a magnitude of 9.503 newtons. And if we looked back at example, or at the solution for part A of this, where we did it with vector addition, we would see that this is the same as from part A. So that means that we're on the right track here, that we haven't made any mistakes yet. Now, we also need to define the angle at which Fr is acting. So let's make up an angle here, call it phi r. Now, that's not hard to find. We know that tangent of phi r is equal to the absolute of Frx over Fry. Now we just put that absolute value in there to ensure that this plus or minus sign doesn't come back to haunt us in terms of determining this angle. Because we're doing this angle quite visually, we don't need to worry about negative or positive signs of the force component values. And we'll put in the appropriate rotation off the appropriate axis manually later without including a sign. And we can rearrange and solve for phi r is equal to the arctangent of the absolute value of our x force component over our y force component. So this gives us phi r is equal to the arctangent of our x value, absolute of minus 6.225, divided by 7.180. And this gives us phi r is equal to 40.93 degrees. So let's draw the summary for that resultant force and draw it with our appropriate sign convention for our rotation, our angle theta instead of phi. So a summary value would have us sketching in our axes here. And then we can go ahead and draw in our force vector, Fr, the resultant force of magnitude 9.503 newtons. we could define, or we could put in this phi value, and we could now specify theta. And we know that theta is simply equal to 270 minus phi. And theta is equal to 270 minus 40.93. Theta is equal to 229.1 degrees. And if we compared this with what we got in part A, we would see that we have the same answer. Which we should, because there's really no difference between the two methodologies. It's just a different way of adding vectors together. So now let's look at part C. We want to find a reaction using FR. In other words, let's find our reaction using our resultant force. Now, what's a resultant force? Well, the resultant force is simply the equivalent single force that would do the same as having all three of our original forces. So let's sketch this out again and see how simple of a problem this is. Let's draw in our x and y axes here. We know we have x and we have y. Now let's draw our force resultant value. Fr is equal to 9.503 newtons. And we know that if we apply a force in one direction to something, we have to resist it by an equal and opposite force. Otherwise, we're not in equilibrium. So reaction. Now, how do we put that down in math? Well, we could do two things. We could look at, let's see, we could go option 1. And in option 1, we'd have force in x y, and y components. Solve for Rx and Ry, then find R and find theta R. Now we could go ahead and do that. Break all our forces down into x and y components and solve for the x magnitude of R and the y magnitude of R, and then find the total magnitude of R using Pythagorean theorem, and then find the angle at which it's acting, and this would be a similar step as what we've done before. That's a perfectly valid option, but we know from observation right away that R has to equal to FR. So let's look at option 2 and see if we can simplify this and still use the mathematical procedure. So option 2. Let's first define a U and V axis. So let's rotate now let's call this the U and this the V axes. And the U and V axes are such that U is along our line of action, and V is perpendicular. And we're allowed to do that. There's nothing stopping us from essentially just rotating our paper and drawing this as an XY system, except for now we're going to call it a UV system. You'll often hear that we're allowed to define our own axes, and that's exactly what we're going to do here. So now let's take sum of forces in the U direction is equal to 0. Well, we have two forces in the u direction. We have R is a positive value in the u direction, minus FR is a negative value is equal to 0. So R is equal to FR. R is equal to 9.503 newtons. So we've solved for the magnitude of that. Now it was obvious just by observation, but nonetheless we've shown it mathematically. Now we could take, for completion's sake, let's take sum of forces in the v direction is equal to 0, and we could just say that 0 is equal to 0. There's no forces in the v direction. Let's look at our angles here. We know we have that phi value. Well, that phi value would also be this angle here. That means that we have our theta r value there. And theta r is simply equal to 90 minus phi. Theta r is equal to 90 minus 40.93 degrees. Theta r is equal to 229.1 degrees. Oh, sorry. I was looking above. Theta r is now equal to is equal to 49.07 degrees. So at this point, we've fully defined our reaction based on the force resultant vector alone. And that's essentially the purpose for calculating these resultant vector forces, is it allows us to simply define our reaction.